The next part we're going to talk about is laws of performance software. It is a little bit, I'm getting on my soapbox and telling you how to run things, but there is a purpose. So suppose that you want to write fast programs and you like checklists as well as handy rules. If so, you're in luck because there is Krista's 5 laws of performant software. Number 1, programming language is much, much less important than programmers' awareness of performance. And honestly, there's no programming language that is magic or good or evil in any inherent sense. You could use any language to write a program that's slow. You could use any language to write a program that's fast. That's not the important part. All programming languages are capable of doing both good and bad. And there's a lot of C elitism in the world, and there's the back in my day sunny people who claim that assembly was best and they had to walk to school in the snow uphill both ways. I'm sure it was difficult for them, and I'm sure they think it was valuable that they really struggled through the little details, but you don't necessarily have to, and that would be okay. High-level options aren't inherently bad or worse or anything than a low-level language. Do I use an array, a vector, a list? Those things are sometimes first-class concepts in a modern programming language in a way that they're not in an older programming language, and you don't have to write your own implementation or find a library implementation of it because they're just built into the library or the standard library of the language, or they're built into the language itself, and that would be okay. Some of those fancy tools are just syntactic sugar. They're convenient from a programmer's point of view, and you can ask, what do they do behind the scenes if they're not very fast, if they're not performing the way that you would expect? And if you browse around, there may be a construct that represents exactly what you're looking for in that language. So if the list that you're looking at isn't very fast or has issues that prevent your program from using it, well, there's probably an alternative to it. There's more than one kind of list. In a Java-like language, list is an abstract type, and there's an array list, and there's other kinds of list, and it doesn't matter which one you use as long as it's appropriate to your scenario. So ask yourself, is there a better way? I put a little asterisk on this in that this is my own thinking, that some languages lend themselves better to parallelization than others, and this doesn't mean that you can't write a program that is a parallel program in C. It's just it might be easier to do that in Rust because Rust does more compile time checking. A language may force a certain way of thinking based on its rules, and if it's a functional programming language, you might have to write in a functional style, and that's enforced on you by the language in a way that it isn't enforced in C, although you could write a functional program in C if you wanted, but it's really up to you, and as I say, Rust encourages you to avoid mutability, encourages you to think carefully about what you're doing, prevents you from doing certain things that we know to be bad, but it's not magic. It's not going to, in that sense, make your program for sure faster than another language would. Rule 2 is nonlinear output, or if you want a mathematical equation on it, it says the difference between f of x and f of y is much greater than the difference between x and y. And that is if those are your two versions of the code, x and y, the performance outcomes, f of x and f of y, are usually much larger than the differences between the code, which is small details matter. In the example here, if you fixed a memory leak, the addition of one deallocation statement, free in a C program, is a single line code change, but in the long run can have a dramatic impact on performance because it is going to ultimately mean you have less swapping, and that and fewer trips to memory, fewer cache misses, stuff like that. Similarly, if you change a configuration parameter from 4 to 8, maybe that actually makes a really big difference in the performance of your program, even though you changed one character. Are you using caching properly? Can you use a different serialization algorithm where you don't change anything in your code at all? You just change what library you're using, and instead of changing a line of code, you just change the thing in the cargo manifest and use faster serialization. That can actually have a very big impact on your program performance. So what I'm saying is, don't overlook the small stuff. If you're faced with a program that is small, you can make lots of big architectural changes and sort of have confidence that everything is going to go fine. If the program that you're looking at is a lot bigger, though, you can't just re-architect the whole program in a weekend and say, hi, look what I did. That's a huge undertaking. It's tempting to think that those huge architectural changes are the solution to performance problems, but there are plenty of gains to be found in the small stuff as well. Item 3, the correlation between performance degradation and unbounded resource usage is very high, greater than 0.9. Oftentimes we focus on functionality. We talk about what features does the product need to have, what things do I need to implement, what needs to be supported. If you listen to a certain kind of product manager, they will tell you that we can't sell the software unless it has the following 847,251 features, and if we're missing any single one, our competitors will clobber us and we'll go out of business, and everyone in the company starves to death in an alley. No. Not really. But this also overlooks the operations side of it. If you want a program that scales, you also have to think about operation and not just functionality. So not just what features does it have, but how does it work and how does it use resources. And so rule 3 is really about you need to establish boundaries. Resources need to be limited in some way. You have lots of memory that is available, but not an infinite amount. You have a good amount of CPU time that's available, but again, not an infinite amount. And you want to enforce limits in your code rather than just run up against operating system limits. Right? If a program starts threads, it's maybe better to have a thread pool of fixed size than it is to spawn a new thread for every incoming request. Because, well, if there are a huge number of incoming requests, you end up creating a very, very large number of threads, and then that could eventually be exhausted, right? The resource of how many threads we could spawn could be exhausted, and then we're in trouble because we didn't prepare for this eventuality. Is there a cache? Well, the cache has to have a maximum size so that the cache doesn't take up an inordinate amount of memory. If you're reading input, reading in a file, reading that to memory, don't use a function that reads an entire line until an arbitrary length, until it gets to a carriage return or end of file character, because who knows how long that could be. If you are receiving a string from a client or something, don't wait for a null terminator. It could be really big. Your program should give design effort to what happens when resource limits are exceeded, or at least we're at those limits. Right? The thing is that there are limits, and if you don't enforce them in your software, you will run up against either an operating system enforced limit or just the limit of whatever you've got in hardware, and you don't want to crash into those without a plan. So you should, for example, set a request queue size. When the queue is full, further requests are rejected in some well-understood manner. You say service is at capacity right now, try again later. That has two benefits. Number one, it prevents clients from calling the service repeatedly and trying to get service that's never going to happen because we're under such heavy load that we are potentially overloading the system. Number two, it also makes the experience better for people who are there getting service, clients who are successful in connecting, and it prevents you from getting everybody unhappy instead of some people unhappy. Thinking back a number of years ago to the launch of the game Diablo 3, on launch day, if you had purchased the game, you had a hard time actually playing the game because you would try to create a game and the servers would say, sorry, servers are at capacity, try again later. Why do this? Well, some people are playing the game. Actually, a fair number of them, I would imagine. And if you just kept spawning more games and running them all on the same servers, eventually it would degrade performance for everybody to the point where everybody's having a bad time. And or crash the servers, in which case that's not good either. Somebody's getting paged on that in the middle of the night, let me tell you. Whereas if you reject people in their request to create a game and you say, sorry, the system is too busy right now, please try again later, some people are unhappy. You trying to create the game, you are sad because you want to play the game and you can't, but that's better than everybody being unhappy. And planning for the idea of there are limited resources, and when those resources are exceeded, we have a known way of rejecting requests, makes it a lot easier for clients to prepare for and deal with that situation, especially if you are writing a specification or you are offering a service where you say, okay, here's what happens under these circumstances. Clients who want to consume that service know what to do and know to expect it as a possibility. Rule 4, do experiments. Science. Yeah, all right, we've covered this already, but it's in the list, and we'll just mention it again, which is if you want your code to be faster, you have to know why it's slow. It's okay not knowing the answers, but you do need to have a way to find out, and as I like to say, don't guess, measure. And rule 5, you can't outrun the fork, which is kind of a pun. No amount of nodes, cores, memory, etc. will save you from poorly written code. Throwing more hardware at the problem is expensive and is in the long run fairly ineffective. It can work in some certain situations, of course, and fundamentally even the best code will need a lot of hardware if you're going to scale it up to millions upon millions of users. But just saying, no, it's okay, we'll rent a bigger Amazon instance, or we'll buy 10 more servers or something, that's kind of an expensive solution, and it can't scale forever. There are limits to how much computing capacity you can afford, so you do have to be a little bit careful about this. And bad code is bad code, no matter how much hardware it runs on.